everyone can see the screen, right? Yeah, so at first I'd like to thank the organizers for giving me the opportunity to speak in this seminar. It's an honor to speak here. So everything that I'm going to be speaking of today is joint work with Jan Zemke. Jan might be also in the audience today. So at first I'm going to tell you about the motivation for this work, how we ended up in the connected sum formula. And then for the majority of the talk, I would be discussing the proof of the connected sum formula, how we can approach this. And at the end, I would be talking about how we can deduce the oriented skein relation for the minus version of instant and not homology. So this oriented skein relation was not really part of the plan, but recently we observed that with all these arguments, if we put all these arguments in properly together, we might just have the oriented skein relation for minus version. Previously, the oriented skein relation existed only for the head version due to the work of Kronheimer and Mrowka. Yeah. So let me start with the motivation. So it is well known in Floer homology. I mean, the minus version, it's a F adjoint U module, and where F is, in instant on it's just C, in the Hegar Floer it's just F2. So it's a F finitely generated F adjoint U module, and structurally it's isomorphic to this infinite. It's isomorphic to this infinite U tower, and plus some torsion stuff. Now this infinite U tower is what gives us the tau invariant, because the tau invariant is by definition the maximum Alexander grading of the non-U torsion element. And we know that this U map keeps dropping the Alexander grading by 1. So the starting point of this tower is the tau invariant. And we also have this stuff, which is the torsion stuff, which by definition is annihilated by some U power K. So in the paper by Ghosh, Miller, and Zemke, they define this invariant called the U torsion order. And it is exactly what you think. It is the minimum of K belongs to N, so that U power K annihilates all of this torsion stuff. Now, in the instant and Floer setup, I was interested in this question: how can we show that the two bridge knots have U torsion order 1? And the reason I was interested in this was, now we have a large surgery formula in the instant and Floer setup due to the work of Lee and Ye. So this fact might be useful in computing framed instant and Floer homologies of large surgeries of two bridge knots. So it turns out that we only need to prove two facts to have the U torsion order of two bridge knots is 1. And this is from the spirit of the paper by Ghosh, Miller, and Zemke. So the first thing one needs to do is one needs to define this, one needs to prove this connected sum formula, which is the topic for today. And the second is the knot cobordism map in the instant and Floer homology. And one needs to prove that if I have a knot cobordism between two knot K and K prime, and if I attach a trivial tube to the knot cobordism, then it increases the genus by 1. So then I have a new surface between the same knot K and K prime. And one needs to prove that the associated map for the minus version for this new surface sigma prime is U times the cobordism map for the previous surface. So every time we attach a trivial tube, the cobordism map changes by U multiplication. So over the last year, we made some good progress in both of these problems. And today the goal is to share the progress we have on this one. So now, I would like to talk about the not Floer homology, but in our setup, sutured manifolds would be an important part of this definition. So I would remind everyone what is sutured manifold, although this part of the talk might be super boring. So for us, a balanced sutured manifold, it's a compact oriented 3 manifold with some oriented multi-curve on the boundary. so that certain conditions are satisfied. So the first condition is this manifold M has no closed components, which is reasonable. The second condition is pi 0 of gamma surjects onto pi 0 of del M. Now, what this means is that we cannot leave the boundary without putting any suture on it. So another way of saying that would be to say that pi 0 of gamma surjects onto pi 0 of del M. And the third condition is this oriented multi-curve splits the boundary into two parts. One is the plus region, another is the minus region. So now, which one is the plus region and which one is the minus? The plus region is the one whose induced orientation is same as the orientation on gamma. And the minus region is the one whose induced orientation on gamma is the opposite of the orientation on gamma. And for us, there will be a fourth condition, which is the balanced condition. So this is the balanced condition, and it says that the Euler characteristic of these two regions are the same. In fact, in our case, all the sutured manifolds would be interested. They will be diffeomorphic. So let's look at some examples. So the point is we can cook up some easy examples of balanced sutured manifolds from a closed oriented 3 manifold Y. So if you have a closed oriented 3 manifold Y, then you can delete a 3 ball from that. Then the new manifold will have this sphere boundary, and on the sphere, any closed, any oriented simple closed curve is going to split it into two disks. In the second example, we are looking at knots inside of closed oriented 3 manifold, and the knot exterior has torus boundary. And if you put two oppositely oriented meridians, it splits into two annulus. And what this third example is saying is that there is nothing special about infinity sloped curve, which is the meridian. So you can take at, if you have a preferred, if you have any preferred longitude of the knot, then you can look at the curves of the slope lambda times n times mu, which we call the slope n curve on the torus. And such curves are also going to split it into two annulus. So this will give us an infinite family of sutured manifolds, balanced sutured manifolds. Now let's very briefly talk about Floer homology. So what is Floer homology? It's an invariant due to Oshpath and Szabo, and also independently by Rasmussen, and it comes in two flavors, the hat and the minus version. And on the other hand, for sutured manifolds, we have this theory of sutured Hegardt-Floer homology, which was constructed by Ghosh, and he showed that the sutured-Floer homology and the Floer homology are, and the relationship is this. So if you have this knot exterior, and if you look at the meridional sutures, then the sutured-Floer homology of this is isomorphic to the Floer homology of the knot. There is also a relationship between the minus version and the Suture-Floer homology, but this is a bit more subtle. So this was shown by Etnayer, Velovic, and Zarevs. So what they showed was, if you consider the infinite family of sutured manifolds we just saw earlier with respect to the negative orientations, and between any two members of the family, then there are two bypasses. So a bypass is a contact structure on T2 times I, a tight contact structure that increases the framing by 1. And there are two of them. They induce maps on Floer homology. So if we look at this, if we look at this horizontal system, and if we take the negative bypass maps and form the direct limit of this horizontal system, they showed that this limit is isomorphic, the direct limit is isomorphic to the minus version of Floer homology. Now, why are we discussing this? The reason is, in the instanton Floer side, we do not have a independent definitions of Floer homology. So these definitions these isomorphisms in the Hegardt-Floer will be the definitions in the instanton Floer homology. So now let's look at the instanton Floer side. So sutured instanton homology and both sutured monopole homology, they were both constructed by Kronheimer and Mrofka. And in this case, analogous to the Hegardt-Floer side, they defined the head version of knot-Floer homology to be the sutured instanton homology of the knot complement with meridional sutures. Similarly, the minus version was defined by Lee. And so previously in the Hegardt-Floer side, we said that, by the work of Etnayer, Velovic, and Zarif, we know that this horizontal system, the direct limit of that is exactly the minus version. And we also have these commutative diagrams that this plus bypass map and the minus bypass map forms. And what this means is that this plus map now induces some well-defined actions in the direct limit. And that is what he calls the U action. So in this, so in the instanton side, the minus version is exactly by definition, it's the direct limit of this horizontal system, and where the U action is coming from the induced action of the positive bypass on the direct limit. So that is how we are looking at this as a F adjoint U module. Now, with all this in hand, we can state the main result that we proved. And the main result that we proved is this minus version of the instanton knot homology is isomorphic to the mapping cone of this map. So both of them are F adjoint U modules. So I am introducing two variables. So this is a F adjoint U1 module, and this is a F adjoint U2 module. And I'm looking at from the usual tensor product of over the field K, I mean the ground field. I'm looking at this map U1 tensor U1 on this coordinate identity here, and the identity here, and U2 here. If I look at this map and then take the mapping cone of that, then that is exactly isomorphic to the mapping to the minus version of the connected sum. And this is also a model for the derived tensor product of two F adjoint U modules. So both of them are F adjoint U modules, and this is also a model for the derived tensor product over the field over say C adjoint U. So before I talk about the proof, let me say why this formula is not surprising. And so in the Hegardt-Floer theory, we know that the connected sum has a chain complex, which is the tensor product of the chain complex for K1 and K2. But when you take homology does not behave so nicely. So there is always a Tor functor in the Kunet formula. When you are working with free group, when you are working with free groups, then the Tor vanishes, but these not-Floer homology groups are not free. So the Tor is always there. And Tor is also known as it's also the derived functor for tensor. And I guess this is just a equivalent way of formulating the connected sum formula. Now, although this statement sounds algebraic, but in the heart of this theorem, there is a topological lemma that we proved. And so I will discuss how we prove the connected sum formula from this point. So the main point is this minus version is defined as a limit. And every time we want to do something with the limit, we pick some element that's close enough to the limit. So let's say that on the left-hand side, I have my knot K1 gamma n. I'm looking at some large enough slope, because so that this member is close enough to the limit. Similarly, on the right-hand side, I'm looking at the knot K2 with slope gamma m, where m is again large enough, so that this is close enough to the limit. And the first question that one can ask is, how can one naturally form the connected sum of the knot complement of the connected sum? And we realize that to do that, what we really need to do is we need to identify the meridional annuli on the left with the meridional annuli on the right. So these two squares, they refer to the boundary torus of the two knot complements, and these rates are my dividing curves. I have on this side I have n twist, on this side I have m twist far away, and this is a local picture. And to form the connected sum, we are identifying these two annulus. It turns out that there are many ways you can do this. In our previous paper with Chen-Kun Lee and Mike Fong, we did it with a contact 1 and contact 2 handle. But in our paper, we do it slightly differently. So what we first do is I have the disjoint union. So now I first change my manifold by attaching to 1 handles. So this is a different manifold than the disjoint union. So I'm changing this manifold to a different manifold. Now in this new manifold is what I call Y, sorry. So this manifold is Y. In this manifold, we realize that to identify this two meridional annulus, all we need to do is we need to attach a contact 2 handle along this knot L1 and also a contact 2 handle along this knot L2. So, and once we do that, once we attach this to contact 2 handles, what we have is the sutured knot complement of the connected sum. Now then what we do next is we interpret our contact 2 handles as surgery maps. So
may I interrupt for a question on that?
Yeah.
So, I mean, somehow topologically, that's of course the same as, if you imagine that you kind of canceled one of the, like maybe the one of the one handles with the 2 handle that spanned L1, that looks just like what you did. That looks like the other construction. In other words, that looks like just adding one handle and then adding a single 2 handle. So is there something different about the contact structure that you're getting on that?
I mean, I believe the context. I mean, are you asking that if the two, I said there are 2 ways of doing that. Are you saying that the context structures are different in both cases?
I'm asking what's the difference. I guess I'm asking what's the difference, and then I wondered, was it somehow because topologically, of course, it's the same.
The suture's different.
Oh, okay. So the sutures go differently around when you do that bypass. So it sort of goes over twice somehow.
Well, it's just the first time you were getting a connected sum with meridional sutures. Now we're trying to get a connected sum with longitudinal sutures.
Okay.
Oh yeah, that's what we are trying to do. Yeah. So in this case, so I'm looking at this. So this minus version, you cannot use the meridional sutures because the meridional sutures.
I didn't want to use the meridional sutures. I just was remarking that if you, I mean, you said add two 1 handles followed by 2 2 handles. That looks rather similar.
So these are, so I'm not really attaching a contact 1 handle here because when you usually attach contact 1 handle on the dividing curve. So so this is not really contact 1 handle. I'm just changing my 3 manifold, the sutured manifold. This is not the disjoint union anymore. I'm not attaching contact 1 handle. Even you have probably already observed that I have this new sutured manifold is not taut because I have a compression curve here. So this cannot be contact 1 handle attachment because contact 1 handle attachment gives you identity map, but this sutured manifold would have 0 homology. So this is not contact 1 handle.
So Danny, topologically, you're right. You could just like subdivide the annulus into different things. Yeah. This is just like the trick that makes the algebra work out, I guess. Is
it as John says that the point is that when you do this surgeries, you're actually doing surgeries in the sutured category. So the sutures are going over in some more complex pattern than as opposed to just the simpler topological thing. Okay, that's fine. Thanks.
Well, I think you can attach a contact. Yeah. So the trick of adding one contact 1 handle and one contact 2 handle, I think you get the right sutures, but like you just can't do the algebra. Like it wouldn't. I don't know. For some reason, this way of doing it makes the algebra natural. So you'll see. I'm sure Sudipta will tell us.
Okay, thanks.
Yeah, I guess what Yan was saying was right. I mean, the goal for this is to prove the connected sum formula in the instanton knot homology. if you do buy a contact 1 and 2 handle attachment, you can surely prove it in the Hegardt-Floer setup. I mean, that was the first proof actually we worked on, we gave on the Hegardt-Floer, but it did not really extend to the instanton Floer. So that's why we are sort of doing it for the contact 2 handle by using 2 contact 2 handles, although this is not really the minimal way of doing it. But somehow it works in the instanton Floer, which is the goal for our work. Yeah. Any more questions? Okay. So now, once we know that these are the 2 contact 2 handle attachments, then the rest is we really need to realize this as surgery. Now, in the instanton Floer side, this basically follows from the definition of Baldwin and Civic. So they define the contact 2 handle attachment map in terms of surgery. You have some attaching cycle of the contact 2 handle on the boundary of the sutured manifold. You push it into the interior of the manifold, and then you do zero surgery with respect to boundary framing. So that was sort of that follows from their definition. There is nothing to prove there. In the Hegardt-Floer theory, this formula was first given by Jake Rasmussen, but to the best of our knowledge, this formula, a proof of this formula has not appeared in the literature. So we first proved this lemma. I mean, one of our goals was to sort of give a unified proof of the connected sum formula that works in all Floer theories. So we also give a proof of this lemma, and then by the virtue of this lemma, the contact 2 handle map, no matter whether you are in Hegardt-Floer or in instanton Floer, it's given by this formula. This 1 handle map, the contact 1 handle map is known to do nothing, because both in the Hegardt-Floer and in the instanton Floer, it's just the identity of on the chain complex. So it doesn't do anything interesting, and this is given by some surgery map.
Does the identity make sense? I mean, like,
yeah. So I guess you mean in the instanton Floer side?
Well, in any setting, I mean, it's the same chain complex. I mean,
so
yeah, okay.
So when you attach a contact 1 handle, I mean, in the instanton Floer side, what you do is these maps are actually defined through cobordism. So you have a sutured manifold, you attach some contact 1 handle, and then what Baldwin and Civic showed was the new manifold has the same closure as the previous manifold. So you did not really change the closures of the sutured manifolds. And these maps are defined through cobordisms between the closures. So they have the same closures, and the map between them is just the identity. So it's just identity.
So is like there's a canonical diffeomorphism between the closures? Is that the statement? Like a canonical diffeomorphism up to isotopy?
Yeah, I mean, the thing is, to form this closure, what you do is you attach some surface times identity on the boundary, but you have lots of choices on the surface. And if you attach some 1 handle, then you can also modify your surface so that then the 2 closures are the same. So there is some canonical diffeomorphisms going on.
Okay, thanks.
So another way of saying it is that you can find one closure, which is simultaneously a closure of the manifold, the original manifold, and then the manifold after attaching the 1.
Got it. Thanks.
And so so then this is just identity. So all the interesting thing is really in the zero surgery. I mean, zero surgery of the attaching circle pushed into the interior of the manifold. And the good thing about this is, once we can say that some map is surgery, we can apply this, this one trick that sort of binds all these Floer homologies together, which is the surgery exact sequence. So then we can apply this thing called the iterated mapping cone formula, which is the generalization of a surgery exact sequence to the 2 component, to the 2 links, I guess. But in our case, we'll be only applying this formula for the link, this 2 component link L we described earlier, which is this link. L1 is this, and L2 is this. So now we are applying this formula. So by the iterated mapping cone formula, there is a homotopy equivalence between the chain complex for 0, 0. By the way, so here I'm looking at the slope n plus m. So the minus version does not have any chain complex, because you are passing to the homology, and then you are taking the direct limit. So the homology of KHI minus is not coming from any chain complex, but this one, by the chain complex, I mean the chain complex with slope n plus m on the connected sum. Okay, so the thing is, so there is a homotopy equivalence between the chain complex with 0,0 surgery with slope n plus m and with this complex. So this complex is stated as a diagram, and what this diagram mean is that it means that this, if you go in this way and if you go in this way, they are not the same, but they commute in homotopy, and the homotopy is given by this arrow, this diagonal arrow. And every time, and these maps are exactly the surgery maps in the QB picture. So for example, this map L1 star what it is doing is it's canceling this one surgery on L1. Similarly, oh, I should have maybe, oh no, it's fine. Yeah, so similarly, this is also canceling the one surgery. Here I'm canceling this one surgery by infinity. And the reason we are doing this notation L2 star star is, the reason for that is the Kirby picture for this surgery exact sequence is you first do 0 surgery and you do a -1 framed meridian of Li, and then you do a -1 framed meridian of the meridian. So that's why we are using this star star. And every time we have this commutative diagram, we can also view this as a chain complex. And as a vector space, this is the direct sum of all this vertex. And the differential is given by using all this arrow. So for example, if you have an element here from 1, 1, you can use the internal differential plus this, plus this, plus this. Similarly for the other ones as well. So you can view this as a chain complex, and then there is a homotopy equivalence between them. So our goal is to use this formula for this. And usually the iterated mapping cone formula could be tricky to use, because if all of them become non-zero, then you have lots of maps between them. But as we said earlier, we changed our 3-manifold to some 3-manifold. The 3-manifold we started with was the disjoint union, and we changed it by attaching these one handles to a manifold which is not taught. So, and this was the compression curve for this manifold. So they are not taught. So R plus and R minus become compressible. So that means when you pass to homology, the Suture Floer homology, then this group has to vanish. And then that will mean that there are not many maps to the zero object. So all of this will go away. And then the only part of this, this formula that survives is this part. So then we have to understand what is this, what is the object 1, 1, what is the object infinity 1, what is 1 infinity, and what are the maps between them. So from now on, we try to understand what are all these manifolds. So if you look at the manifold 1 infinity, so all this manifold 1 infinity, 1, 1, and also infinity 1. The infinity 1 is not drawn in picture, but it's also similar to the other case. So they all refer to the same sutured manifold. The only difference is that the suture is different. So for example, for when you are doing one surgery on L1, this dividing curve is passing through the suture L1, and you are doing one surgery on this attaching circle. So the effect on the suture is a dent twist along the attaching circle. Similarly, when you are doing the L infinity 1, nothing happens to this suture, but this suture would have a dent twist along L2. And in this manifold, I'm doing this, 1, 1 surgery. So that means both of the suture are now taking dent twist. Both of them are taking dent twist. So it's going like this, coming like this. I probably lost track of the curve, but yeah. So all of them are sutured manifolds, and to understand these groups further, we can do some disk decompositions. So for example, this group is very easy to understand because we can literally see that there is a contact one handle attachment here. and the dividing curve is being extended in the contact one handle. So what we can do is we can cut along this disk. This disk intersects the suture in exactly 2 points, and that is called Productivist Decomposition. And both in Heckert-Floer and in instant-on Floer, this Productivist decompositions are isomorphisms, because they are the inverse of the contact one handle map, which is known to do nothing. So this Productivist decompositions will give me isomorphisms. I have n twist on the left and I have m twist on the right. So if you cut along the product disk, what you get is this thing, Cn tensor dm, where Cn is the knot complement with slope n, and dm is the knot complement with slope m. So when you cut along 1 infinity and infinity 1 by exactly the same argument coming from this product disk, we have this isomorphism. And for 1, 1, you can also do the same thing, but here the compression curve you see intersects the suture in 4 points. And in this case, there is, by a theorem from a previous paper by Jinkun Lee and myself, this resulting thing is direct, it's isomorphic to the decomposition along D and the decomposition along D bar. D bar is the disk with the opposite orientation. So if you do 2 disk decomposition with D and D bar, then the suture Floer homology of that would be isomorphic to the suture Floer homology of this gadget. When you round suture, you might have some compression curves. So you have to throw them away if they are not taut. But at the end, what you will have is Cn minus 1 tensor dm plus Cn tensor dm minus 1. And so this is what you have for this manifold 1, 1. And so once we understand what are all these groups, then the rest is to understand what are all these maps. So in the formula, we have this map from 1, 1 to 1 infinity 1 and 1 infinity. So we have to understand all these maps, and there are not many maps actually you can guess between these 2 objects. So if the only guesses maybe we can make is that they are the bypass map, which increases the framing by 1. So next what we do is we prove that this guess is indeed right. These maps are the bypass maps. We have to check the signs, but so what we do next is to understand the maps between them. So in this case, I'm looking at the map between y1, 1 to y infinity 1. And so the picture is wrong. This curve should be L1 star star. I thought I would change it, but then I forgot. So this is L1 star star. There is a typo here. What this is doing is this is canceling this 1 surgery on L1. So this is going from y1, 1 to y infinity 1. And as we said, the PV picture of this canceling the 1 surgery is exactly the -1 framed meridian of the meridian. And when you handle slide, then the surgery curve becomes handle slide equivalent to this curve that goes from the left and right like this. So this is my surgery curve. Now, the guess is that the map is the bypass map, but the bypass is sort of happening in one side, but this curve is going from the left to the right. So, and also this is going through the decomposition disk, which is something that we don't like because, we are using this iterated mapping cone formula, but there are also these disk decomposition isomorphisms. So we don't like this, that this is going to the decomposition disk. So we apply some trick. So we see that this attaching circle remains parallel to the suture for most of the time. So for example, if you from this point, this attaching circle, this dotted circle is parallel to the red curve. So every time you have this, what you can do is you can attach a contact one handle exactly on these two red points and bypass this portion of the attaching circle into the contact one handle, into the core of the one handle. So on the right picture, so we are doing is we are attaching two contact one handles in these 2 points. And we are bypassing this portion of the arc into the core of the contact one handle. And the reason you can do that is because, as we said earlier, this contact one handle attachment does not give you anything interesting. The closures of these 2 sutured manifolds are the same. So the associated closures are the same. And in that closure, this attaching circle and this attaching circles are isotopic curves. So they give you the same map. So we are doing this isotopy of the attaching circle for the 4-dimensional 2 handle in the closure. And then once you do this isotopy, then you can cut along this disk and have this product isomorphism, and your attaching circle is exactly on the right hand side of the picture, and a bypass is also a contact one handle followed by a contact two handle. And this is exactly the contact attaching circle for the bypass of the the attaching circle of the contact two handle in the bypass attachment. Or this is the bypass arc in the knot complement. So this is how we realize this surgery map as a bypass attachment. So here we are just doing it for 1, 1 to infinity 1, but all these arguments are very similar. So this is the lemma that we state, that this map L2 star star restricts to U tensor identity on this, and identity tensor U on Cn tensor Dm-1. Similarly, one can show this. I mean, one only has to check the sign of this bypass attachment. I haven't really put any orientations on the suture, but one can check the sign of these bypasses, and then that's what we have. Modulo signs, maybe. Yeah. So once we understand all these groups, then the rest is then what we do is we are using this iterated mapping conformula, and in the iterated mapping conformula there is a quasi isomorphism. So on the left I have the zero surgeries, and on the right I have this iterated mapping conformula. And this quasi isomorphism is it has length 1 and length 2 maps. So the length 1 maps are dictated by these solid arrows, and length 2 maps are dictated by these dotted arrows. In the Hegardt-Floer theory, this length 1 maps are compositions of holomorphic triangle maps, and this map has holomorphic quadrilateral maps. In the instanton-Floer theory, these are usual cobordism map. These solid arrows are usual cobordism map, and this one has maps that count solutions, index -1 solution in a 1-parameter family of matrix that realizes the different ordering of handles. So what we do now from this point is we prove that this quasi-isomorphism is grading preserving. So in the Suture-Floer homology, you can use any properly embedded admissible surface to define an Alexander grading. So on the left, we have an Alexander grading, and in each of these gadgets, which are basically the knot complement with some slope, you can also use a cipher surface for the knot K1 and the cipher surface for the knot K2 to define a Alexander grading in all of this piece. And we prove that these maps are grading preserving. So you see that here I have a shift. So because this is the domain of the this is the domain of the derived tensor product, and there is always a shift in the domain by -1. So we prove that all these maps are grading preserving with respect to the grading coming from the cipher surfaces of the knot. And once we show this, then the rest of the argument is it's just a formal consequence.
Oh, Sudipta, so, also the zeros are the grading changes, not the map.
Oh yeah, these zeros are the grading changes. Oh yeah, I did not say that. Oh yeah, it's very confusing the way I have said this. Yeah, So by 0, we just mean that this is the shift, because this is a quasi-isomorphism. So these maps are not 0. I mean, it might look like it is 0, but it's just the grading shift. I mean, if you do not have this shift, then you have just these maps, these gradings are just 1 if you do not have the shift, but you have to have this shift to make it grading preserving. Yeah. Is there any question about this? So yeah, so the proof, basically in the proof, you just have to keep track of the grading surface and the attaching cycle of the cobordism, and see how you can make the attaching cycle disjoint from the grading surface, so that the grading surface survives. But yeah, but it's sort of like a homology argument. And the rest of the argument, it's just a formal consequence. I mean, so that's how we prove the connected sum formula. And as I was saying in the beginning, we realized a few days ago that we can probably also use the same argument to prove the oriented skein triangle for the minus version of instant and not homology. So maybe I would, in the remaining time, I would say how we do that. So here is the idea. So in the head version, we have a oriented skein relation due to the work of Kronheimer and Mrofka. So, and here is what they did. So in the head version, the knot for homology is the sutured instanton homology of the knot complement. So these are the knot K plus, K minus, and this is K0. If you look at the knot K plus, then if you take this knot, this unknot, encircling the crossing, so what they do there is they do this infinity, -1, and 0 surgery on this knot. When you do -1 surgery, you get to K minus, which, and so the if you do a -1 surgery on the sutured knot complement of K plus, you get to the sutured knot complement of K minus with the meridional suture. So this group is exactly what it should be. But when you do 0 surgery, you don't really get the knot complement for K0. You get, so what they do is they do a product annulus decomposition. So they do a product annulus decomposition. And it is known that both in Hegardt-Floer and in instanton Floer, the product annulus decomposition always gives you isomorphisms in homology. So by Floer surgery exact triangle, all these terms are exactly what we want, and then they do a product annulus decomposition to get that this is exactly the two component. This is exactly the link complement K0. So that is how they prove this. Now, when you were dealing with this minus version, then you don't really have you are not dealing with the meridional sutures. You are dealing with the sutures that sort of wrapping around, along the knot, some number of times. So in this case, you can run the exact same argument as they did in the head version. The only problem is it's not clear what to do with this 0 surgery, because you can't just do a product annulus decomposition because there is no product annulus. But as we were discussing earlier, this annulus is still there. It's just not a product annulus anymore. So here is what you can do. You can, instead of thinking of sort of like a decomposition like theorem, what we can do is we can look at the link complement of K0. So let's just focus at a simple case where K plus is a knot, K minus is a knot, and this is a 2-component link. And what we want to do is we want to identify again the meridional annulus together, exactly the reverse of this map. So now by exactly the same argument that we ran earlier, so on the left I have this link complement, one component of the link K0. This is one component of the link K0, and we are identifying again these two meridional annuluses, and we are doing it again by the exact same way we did earlier. And so then we can again run the iterated mapping cone formula argument. I mean, here the only difference is that this is the link complement of K0, but earlier we were dealing with the disjoint union of not complement. So if you are dealing with the link complement, there is not much change in the argument. I mean, it seems to us like all the argument just goes through, and you can prove using the same argument, we can prove that the limit homology of the zero surgery, is isomorphic to the cone of this map. U1 plus U2 going from KHI minus of K0 to KHI minus of K0. This is exactly what we proved by the connected sum formula. And this is also, and by the same argument, we can also have this. And in Oswald-Zavos, oriented skein triangle, they proved exactly the same thing. Although what they said was the mapping cone of this map, is quasi-isomorphic to the mapping cone of this map from K0 to K0 given by U1 plus U2. I mean, it has it's a link complement, and in both components you have a U1 action and U2 and on the other component you have a U2 action. So, and that is what they showed. So by this, by this iterated mapping cone formula argument, we can again deduce the same thing, that this third term in the oriented skein triangle is the derived tensor product of KHI minus L tensor with this C adjoint U1 comma U2 mod out by U1 minus U2, and in the over C adjoint U1 comma U2. In the Hegardt-Floer theory, what Oswald-Zavos does is, they use the chain complex for the minus version mod out by U1 minus U2. But in the Hegardt-Floer theory, these two are quasi-isomorphic. So that is what we are claiming. So the exact sequence that we have for a knot K plus, where K plus is a knot, K minus is a knot, and K0 is a two-component link, the exact sequence we have is this, and the third term is the derived tensor product. And what we don't have at this moment is this, all these maps are supposed to be U equivariant, because you have this U action on K plus, U action here. Here you can define a U action, like you can do this U tensor identity. I mean, you can just multiply by U on KHI minus and just do nothing on the right. So you can define a U action here in this way, but we don't really know if this map is U equivariant with respect to that U action. And the reason for that is, we are using this iterated mapping cone formula argument here, and this quasi-isomorphism from the zero surgery, this quasi-isomorphism from the limit homology of the zero surgery to this thing, we don't really know if that map is U equivariant with respect to that U action I just said. But we are hopeful that maybe we can do this. We have some ideas. So we are hopeful about that, but we have this, at least without the U action on here. So that is what we can prove. And this is the conjecture I just mentioned earlier, that this quasi-isomorphism arising in the iterated mapping cone formula is U equivariant. And yeah, I mean, we have some ideas, and we are hoping that we can do this, but I would just say that it's in progress. And yeah, so that's more or less what I had to say for today. So yeah, thanks for your time.
Are there any questions?
Has anybody thought about, so in the Hegardt-Floer setting, Eftekhari and Al-Shahi have this kind of it's not exactly traditional chain complex, but some kind of, twisted complex in the setting of Suture Floer homology in the kind of minus version. And has anybody thought about sort of recasting that in a kind of direct limit and adapting those methods to define analogous invariants in the other settings?
Yeah, I have not personally. I mean, I'm not familiar with their work.
Yeah, I'm not so familiar with it that I can sort of
but like, do they have
say whether that would work or not. But what's that?
Are they working with the chain complex? I mean, many of
No,
this.
it's obstructed. I mean, I think is the issue. When you have sort of more interesting suture manifolds. But it's like I don't know, it's like some kind of, probably you can phrase it as like a type D structure over some ring. I don't know. I was hoping that somebody in the audience would be able to say something a little bit more definitive than that. Or if you, maybe had you thought about it, but anyway, not exactly on topic. So my apologies.
Do you know what paper is that? Sorry, it's not a good question, I know.
Oh, I don't know. I don't know if I know the title, but I mean, it'd be easy enough to find while somebody else asks other questions that are sort of maybe more relevant. I'll Google it.
So maybe I ask a question. I'm not sure how relevant it is, but so this in the extension of oriented disconnect triangle that you talk about. So in the context of figure of Floer homology, so can you remind me how is the link invariance supposed to be related to the invariant of notification? So is it supposed to be something in terms of the notification of your knot?
So
your link.
So are you asking what we have here in the
Yeah. I mean, is that
so they have this thing CFL minus of let me just, I think what they have is H of CFL minus of K0 mod out by U1 minus U2.
What you wrote on top. Yeah, but is that
in the hat version, it's just the notification.
It's a not, but not in the, I'm asking about other versions like plus version. Is it related to notification at all or no?
Well, the thing that actually appears in the exact sequence is the notification. And then kind of what we did was we showed it was this link.
Oh, okay. All right. So this is exactly the notification. Okay.
Yeah. So the theorem, I guess, is like showing that the notification is isomorphic to the normal, the link invariant as you might define it without.
Mm-hmm. Dave, I think you're muted.
Yeah, I was not having anything useful to say. I was turning on my video to pretend to be sociable.
So your motivation initially, can you remind me? So there was a question about two bridge knots that you were
so
trying to attack.
The thing is, I mean, the reason. So what we are trying to do is, So where is it? I was interested in this thing. I mean, it's known in the Hegel-Floer theory. It's due to the work of Ghosh, Miller, and Zemke in their so from their paper. I think the argument is that if you have k connected sum k bar for a two bridge knot, then you have a cobordism between them that is just the identity cobordism attached, and then you attach a trivial tube to that, and then by this fact that this tube attachment has to be U multiplication, and the map is sort of factoring through the unknot. So, and unknot has no U power, I mean, no U torsion order. So it has to kill the, the thing that is factoring through. So, I mean, the U torsion order, the U order for k connected sum k bar, I guess, will be, less than 1. And if you can prove the connected sum formula, then that would say that the U torsion order for k connected sum k bar is same as the U connected, the minimum or maximum, I guess, the U torsion order of k and k bar, but they have the same U torsion order. So, yeah, I mean, so that's how you can basically prove that. So this one would follow from the connected sum formula. I mean, to say anything about the U torsion order, you have to use the connected sum formula. And the other thing follows from this fact that if you have a tube attachment, then this map will be just U multiplication times the previous cobordism map. So this is a result by Jan Zemke and Andras Ghosh, I think. I'm not, this is a result by Jan. So yeah, I mean, with these two, by these two things, it just follows. I mean, previously, before the connected sum formula, we had this proof of additivity of the tau invariant, but there we were just using this thing that I was talking about earlier, which is a contact 1 handle followed by a contact 2 handle. But there you were just looking at the map on the infinite U tower. You were just forgetting about the torsion stuff in the Norfolk homology. So that doesn't give you anything. We still don't have this, because we don't really know if the quasi-isomorphism in the iterated mapping cone formula is U equivariant or not. Because, I mean, there is this stupid, you can define this, this stupid U multiplication map on the derived tensor product, but potentially you could have like the U multiplication on the derived tensor product could be non-trivial, could be something crazy, because we are potentially using this box tensor product of two infinity modules, and so it depends on the bimodule structure on the knot. And I guess we haven't yet properly showed that this map is equivariant. So this part is, we don't really have this at the moment, but that was sort of the goal.
Here's a question. I mean, is this related to the question of whether you can have I'm not going to be able to formulate this property, but this sort of thing came up in a different context. I thought I had the feeling that F adjoined U was simple enough that you could show by algebraic means that you can have interesting like A infinity module structures over that sort of ring.
Oh, John, I can answer the question.
Yeah.
Maybe. Yeah, so it's actually like not too hard to show that like every A infinity module over F adjoint U is formal, like it's quasi-isomorphic to the one where you forget all the A infinity actions. But if you wanted to find the U action on HFK minus, on the tensor product, let's say, you actually need a A infinity bimodule structure on your knot on HFK minus of K. So you need a bimodule structure, because when you take a direct tensor product, the thing you like in nature, it always uses up the module structure when you take a tensor product, since you need another one. But you can definitely have non-trivial A infinity bimodule structures over F adjoin U. And so we have some scheme to show that the bimodule structure is like formal as well, but we haven't written any details down.
Okay, thanks.
So for this question, is there any further topological motivation behind this question? It's supposed to be something about, you know, a structure of instanton not Floer homology.
Which question you meant?
I mean, this the one that you have on this slide.
You mean, oh,
Do
this
you
one?
have some secret? Yeah. Do you have some topological application in mind as a result?
Oh,
of
so
this,
I mean, I think John can say better about this, but I think I heard from him like in a year ago that this fact could be useful in computing framed instanton for homologies of surgeries of two bridge knots, I guess.
Yeah, so I mean, I you know, a year ago, I was wanting to define a surgery formula and then be able to apply it to like alternating knots to compute the framed instanton homology of surgeries. And if you know the U-torsion order is 1 and your knot is alternating, then you should be able to compute, you should be able to compute it from the Alexander polynomial. And then for two bridge knots, there's this nice geometric way of showing U-torsion order is 1 using the Ghosh, Semke, Miller ideas. But yeah, the motivation was just to compute the framed instanton homology of surgeries on two bridge knots and say it's the same as what you get in Hagar-Floer homology.